So good evening, everyone, and welcome to this class. We were dealing with electric flux in the previous class, and we had done some questions on electric flux, and I think this was the most revolutionary one which we did. And the last part was the one where you had to understand what is varying and how it is varying. We remember this question? Now, this will form the basis of everything that we do because the last part of the question was the most difficult question that can be ever made in this category. And I have not seen a question like this in JEE Advanced even. So you might not get this. This was just to make you understand what is fixed and what is variable. Do you understand this from that question? Remember this? Yes or no?
Sure.
Okay. Now, we also saw a very beautiful concept here, and this concept was here, which is marked yellow. Whenever you had this closed surface and it was placed inside a uniform electric field, you found out that the net flux, the total flux was zero. Yes or no? Huh?
Yes.
We understand this? Yes or no?
Sir.
That the total flux was zero, and based on this concept you can have pretty good questions, and I'm just taking a snapshot so that for example, now if this is a question, so we'll start with this question and I'll open that exercise sheet as well and see if I have more questions here. You have this semi sorry hemispherical cap. This is hemispherical cap placed in a uniform electric field. E is the uniform electric field. I think we have done a question like this before where I had put a point charge and I asked you to find out the electric flux to the curved part. Here also the same thing is done, but here instead of the point charge, we have a uniform electric field passing through this cup. Now this cup could be kept like this or at any particular angle, doesn't matter. The essence of the question remains the same. The question is, what is the flux through the curved part of the hemispherical cup? How do you find out the flux to the curved part? And if I can just color it, I've started to love coloring, so I will color it beautifully. What is the flux through this curved green part of the hemispherical cup? I'll give you a minute to do this. And I'm expecting such questions in the exam. JEE Main or JEE Advanced, likewise. Give you 2 minutes to think about it. Remember, whenever I give you a question, I have told you something that will help you in solving it, and I know that you can solve it. Then only I give you a question. I never give you a question that you cannot solve. I will never give you that question that you cannot solve. I only give you that question which I know that you can solve. So there must be something that I've told you that will help you in solving this question. And since the class has begun just now, whatever I've told you probably just now would be good enough to solve this question. So that's the hint. Solve it. If you're not able to do it, let me know. I'll help you out. I would love not to help you out, but if you're not able to do it, I would definitely step in.
Sir,
Yes.
Q by 2 epsilon naught.
How come I don't see any Q? I don't see any Q. The only thing I see is the radius R, which is given here. The only thing that is given to you is the
E into
radius.
2 pi r square.
The only thing that is given to you is the radius R and the value of electric field as E. So you get your answer in terms of E and R.
E into 2 pi r square.
E into 2 pi R square. How did you get this answer?
Have the electric field E.
So electric field, yes, electric field is E, I can see that. And you got the answer as E into 2 pi R square. So basically, you are getting the same answer as this. I love this diagram. I don't know why. I've made it so good. That the drawing is so good. I was very bad at drawing. Anyways, so you say that this question and the and this one are same because you're getting the same answer. No. That was in terms of Q, na? But how did you get this answer? E into 2 pi R square. There was a special condition in this question, and that special condition I told you, all the angles were equal. Yes or no? There was a special type of case here. All the angles were equal. Now, if you come back to the question here, see, they have also drawn a ds. If you look at this area vector, it is at a different angle with this electric field. If I look at this area vector, this will make a different angle with this electric field. If I take an area here, it will make a different angle with the electric field. If I take an area here, it will make a different angle with the electric field. How did you get 2 pi R square? Do you understand what I'm saying? Yes or no?
Yes, sir.
So you cannot get 2 pi R square. The only way you could have got E into 2 pi R square was if the question was like this. If the question was like this, question was like what? Question was like the previous one. Here the answer is E. This is E. Ding 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 ding. This is E and multiplied by 2 pi R square. Here the answer is E multiplied by 2 pi R square. But this electric field is different from the electric field that is drawn there. Yes or no? So the answer cannot be into 2 pi R square. Then what is the answer? That is the question. What is the answer? I must have told you something that that would help you in solving this question. And the only thing that I told you in the class today is in yellow. That is the only thing I told you. Yellow, yellow, yellow. And how do I use this yellow? Here. So how do I use this yellow here? Is I make this yellow. So I color it yellow. I love coloring, so I will color it nicely. Yes, so I make this yellow. Now remember, this was an open hemispherical cup. What I have done is I have put a yellow cap onto it. This yellow cap is actually not a part of the actual diagram. I have put a yellow cap onto it. Now what happens as soon as I put this yellow cap onto it? As soon as I put this yellow cap onto it, what happens? If you just imagine this as your hemispherical cup, it's not it's not hemispherical actually, but it's open from here. So basically the question was like this. If this hemispherical cup is like this is the open side, you can see an electric field going ding 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 like this. What is the flux through this hemisphere? What I've done is I put a cup here. Oh, boom. What happens when I put a cup like this on this? What happens? What happens? If I put this yellow cap on that hemispherical thing,
Closed surface.
It becomes a closed surface. Yes, it becomes a closed surface. And as soon as it becomes a closed surface, the total flux through this closed surface becomes
0.
that's it. So the flux through this closed surface is 0 now. And that gives you the answer straight away. Because this closed surface is placed in a uniform electric field, flux through this closed surface is 0. Now this closed surface consists of two surfaces. As you can see, I've colored them nicely. The flux through the green surface, which is the curved part. I don't have a yellow ink, so let me find out a yellow ink. Okay, this looks like yellow. Plus flux through the circular part. The flux through the circular part is this one, and the flux through the green part is this one. That should be equal to 0. Do we understand this? Now I have to find the flux through the curved part, which is a difficult task because the angles are different, but I can very easily find the flux through the circular part. So I can write flux through the curved part will be negative of flux through the circular part. Do we understand this? And to find out the flux through the circular part is very simple, because now the question is, this is the circular part, and electric field is going dung, 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 dung like this, and the angle between this area vector and electric field is 0. No, not 0. This vector is going here, electric field, this area vector is going like this, and electric field is going like this. So angle is 180 degrees. Do we understand this? But angle is constant. So what is the flux through this curved part, the circular part? What is the flux through the circular part? It is simply equal to E into pi r square. Do we understand this? With a negative sign, because the area vector of this gentleman will go like this. Am I making sense, or is it all going above your heads? Yes or no?
Standing, sir.
So the flux through the circular part is minus E into pi r square. So the flux through the curved part would be plus E into pi r square. And that is your answer. The flux through the curved part will be E into pi r square. That is how you use the information, or what you have understood from the simple example. You can solve many difficult examples. Do we understand this? Yes or no?
Sure.
Yes, sir.
Now, if you understood this, then you can understand that no matter what type of surface is given to you, this is an example. I have seen a question where they had given a paraboidal surface. Paraboidal surface is like this. It's a surface which is formed by rotating a parabola. We like this. That's the paraboidal surface. You have seen parabola, no? In maths, parabola. It's completed, no? Parabola y square.
Completed,
So
sir.
when you rotate parabola like this, it becomes a paraboidal surface. So I've seen a question in a JEE where it was a paraboidal surface, but again the paraboidal surface will have a circular part, and they ask what is the flux through the paraboidal surface. The answer is very simple. The paraboidal surface is open, you put a cap down, the flux through that circular part is a negative of flux through the paraboidal part. Do we understand this? So whether it is paraboidal or any shape, the answer still remains same. Do we understand this?
Yes, sir.
So that is how you use what you have learned and you put it to good use. Am I clear with this concept? Have you understood this? Yes or no? Huh?
Sir. Yes, sir.
Let me see if I can get any more good question on flux, if they are available somewhere. Electric potential, potential. Potential, dipole, electric field line, flux, hemispherical, तो करा ही दिया मैंने. No, I think we have covered everything. Okay, that is the same question that we had done. Okay, we are done with this. Now let us move ahead in life. And how do you move ahead in life? Move ahead with a concept which is known as the solid angle. What is this solid angle? Anyone? Any idea? Solid angle? Solid angle. Have you heard this term, solid angle? Anywhere? Huh?
No, sir.
No, you not heard this term, solid angle?
Great.
Okay, I'm looking for a diagram. If I get that is better. I have got this diagram. Okay. First of all, let us talk about liquid angle. What do you mean by liquid angle? It's not called liquid angle, it's called plane angle. Everyone knows what a plane angle is, yes or no? Everyone knows a plane angle is. Everyone knows what a plane angle is? Yes or no?
Yes, sir.
What is a plane angle? This is what a plane angle is. The angle subtended by any arc of a circle at the center, that is the plane angle, and everyone knows if this arc length is dl and the radius is r, the plane angle, small plane angle d theta will be dl by r. Everyone understands this? This is not solid angle, this is plane angle, the angle that we always use. It's basically a two-dimensional concept. Is the angle that a two-dimensional body, a line is a one-dimensional body, in fact. But a line, whatever angle, or an arc of a circle, whatever angle it subtends at the center of the circle, that is known as the plane angle, and that is the angle that we are using. The SI unit of this plane angle is radians. You know about this, yes or no?
Sir.
Do you understand this?
Yes, sir.
Now, similarly, we can we can extend this concept of the angle formed by an arc to the angle formed by a line at any point, like this. This concept is similar to the angle formed by a line at any point, and to make it more precise in terms of the direction, it is actually written like this. So I hope you can see this. This is a point that is given to you. This is a point that is given to you, and this is a line segment of length dl that is given to you. Now you have to find the small angle d theta that this line segments subtends at the point O. Now how do I find this angle? I join a straight line from O to the center of this line, and we call this as r unit vector. This is n unit vector which is perpendicular to this line, and if I call this angle as theta between the two, because they may not be in the same direction. This r vector and this n vector may not be in the same direction. Basically what it means is, if you have to find out the small angle that this line subtends at this point, here also we are doing the same thing. Here also I am joining it by this, but this dl and this r in this dl and this normal vector are in the same direction. Do we understand this? This n vector of this line is in a different direction than the r vector, but for an arc of a circle, they are in the same direction. So if I extend this terminology to a line, the plane angle subtended by a line will be given by this formula. It is dl into cos theta divided by this length r, which is, you can call it as the radius of the circle. So a plane angle is an angle which an arc or a line subtends at a point. We understand this? And this is how you find it. No one is going to ask you this. So just have to see it as a concept. This is a line. This is a point. What angle this line subtends at this point? This angle is known as the plane angle. Do we understand this? Do we understand this?
Yes, sir.
I call this plane angle as a one-dimensional angle. It's in one dimension. One dimension. But now what happens if instead of a line, which I think is a one-dimensional object, you have a surface? What do I mean by a surface? It could be anything. This helps me a lot. If it is a surface, this is a surface, two-dimensional body. Now, this is a surface, and then this is a point. Now, I can also find the angle that this surface makes at this point. And the best way to imagine it is the cone of ice cream. You see cone of an ice cream? And imagine that cone is completely filled with ice cream. You don't have to eat it right now. Just have to imagine it to understand what is a solid angle. What is a solid angle? Imagine a cone of ice cream. Has everyone written this? Yes or no? Has everyone written this?
Sir, 1 minute.
Okay. Let me know once you're done. Shall we move ahead?
Yes, sir.
Boys, everyone is done? Now,
No, sir.
okay, you are noting it down? Okay, note it down. Let me know once you're done, bacha. Why I'm taking so much of effort in doing this? Because this is going to help us solve a lot of very so-called difficult looking problems very simply. That is why I'm putting in so much of effort. Otherwise, I could have just given you the formula and moved ahead in life. Yes, done?
Done, sir.
Okay. So now we come to this. Now imagine a sphere This is a sphere and you have taken a small segment of that sphere. That small segment has an area dA. Now this area dA subtends some angle at the center of the sphere. This angle is known as a solid angle, and this solid angle is like this. Imagine this is an ice cream cup. This is an ice cream cup which is full of ice cream, pink one. So what I have done is every point on that surface has been joined to that cone of the apex. Every point on this surface is joined to the cone of the apex. So what you have is an angle that comes. You understand? The angle that comes. That angle is known as the solid angle. Solid angle is subtended by areas at a point. Plane angle is subtended by length at a point. Do we understand this? Solid angle and liquid angle, solid angle and plane angle.
Yes, sir.
So this solid angle is represented by omega, oops, wrong color, d omega, and the SI unit is steradian. It's not radian, it is steradian. D omega is dA divided by radius square, if it is a part of a sphere. Because here also, if I draw this this r vector, this r vector or unit vector r and this your dA vector will be in the same direction. I hope you are getting what I'm going to say next. What I'm going to say next or draw next is this diagram where they may not be in the same direction. Where they may not be in the same direction and they may be going in different directions. Here, I hope you can see this. Here your area vector is going in this direction. The pink area vector, ding, 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 ding. And I love to color these days. This pink area vector is going in this pink direction. Do we see this pink direction? And this r vector is going in this green direction. Ting, 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 ting. So again, we have an angle between these two, theta. If that is the case, then this d omega, the small solid angle, is given by this formula. It will now be equal to dA cos theta divided by r square. Do we understand this? Yes or no? Huh?
Yes, sir.
Note it down. I'll give you 2 minutes. Let me know once you're done, bacha. Boys and girls together.
Done, sir.
Everyone, sir?
Yes, sir.
Boys? I'm not getting
Completed, sir.
Completed, sir.
Okay. Now, the next thing that you have to understand is if you have any type of closed surface, any closed surface, the angle that it subtends at any internal point is going to be 4 pi steradian. So that is what you will write. Any closed surface any closed surface, any closed surface at any point which is internal, the total angle subtended by this will be 4 pi steradian. Any closed surface at any point which is external to it will subtend an angle 0. Why will it subtend an angle 0? Why will it subtend an angle 0? Because as soon as the surface become close and close, as you can see, when this is an open surface, as long as this is an open surface, it subtends some angle. But as soon as the surface becomes close and more closed, it becomes more and more close, the solid angle becomes 0, 0, it becomes less and less, and it becomes completely closed, the solid angle becomes 0. Do we understand this? So at any external point, the solid angle would be 0. It is same as saying any closed loop, at any point which is internal, any closed loop with any point internal, how much angle will that closed loop subtend? Closed loop. How much angle will a closed loop subtend? How much angle will a closed loop subtend?
4 pi steradian.
Closed loop at any internal point. Loop, not area. Loop, not area. Loop, not area.
2 pi.
Any closed loop. Any closed loop at any internal point will subtend how much angle? It's not so difficult that you are thinking. Two pi, it will subtend an angle of 2 pi. What is the angle subtended by a circle at the center? 2 pi. If you have a square, what is the angle subtended by a square at the center of the square or any point inside the square? 2 pi. You have any random shape loop at any internal point, the total angle it is going to subtend is 2 pi radians, 360 degrees. Do we understand this?
Yes, sir.
So whatever is true for a closed loop, the same thing is true for a closed surface. The only difference is, in case of a closed loop, we have plane angle. In case of a closed surface, we have solid angle. Do we understand this?
Yes, sir.
Plane angle, solid angle.
Sir.
So what is the answer for this one? At any internal point, the angle will be 2 pi radians. Then can you tell me at any closed loop at any point which is external, what will be the angle? The angle would be 0. As soon as the loop becomes close and close, the angle becomes closer to 0. And when the loop closes permanently, the angle becomes 0. Do we understand this?
Yes, sir.
Okay. Now, why we have spent so much time on this? Because you will have to remember a result. And what is the result that you will have to remember? So again, I will show you a good diagram if you have. Let me find out a good diagram from here. There must be a good diagram that I can show, and I can just color it. Not here, maybe here. No, maybe here. Okay, this one. No, this is. Anyways, I can You can give this one. Now, what do you see here? Is a disk. Disk is a two-dimensional object. Yes or no? Now, this diagram is given for dual purpose. It has got two purposes. The disk, and let us say this distance from the center of the disk is L, and the radius of this disk is R. I'm just trying to write this. Now, this disk is a surface, and I have a point P here. Now, this disk is like the circular part of your cone. This disk is like the circular part of your cone. Do we understand this?
Yes, sir.
Now, this disk subtends a solid angle at the apex of the cone, which will be given like this. Yes or no? Do we understand what I'm drawing here? I'm drawing the solid angle subtended by this disk at the apex of the cone. Do we understand this?
Yes, sir.
And I will not go into the derivation part because you will not get anything from the derivation. The solid angle, you must remember that the disk substance at the center of the apex is 2 pi into 1 minus cos phi. 2 pi into 1 minus cos phi. Now you would be wondering, what is this phi? You would be wondering, what is this phi? So let me tell you what is this phi. This phi is the semi-vertex angle of the cone. 2 pi into 1 minus cos phi is the solid angle subtended by this disk at the apex of the cone. Do we understand this? Okay. Now, this is the solid angle. Now, how are we going to use this solid angle? You just draw the solid angle subtended by a disk. Have you written the solid angle?
No, sir.
Okay. Write it.
Done, sir.
Everyone has written this?
Yes, sir.
Now.
Sure.
Okay. Now, if I go about and tell you how do I find this solid angle? How do I find this solid angle? So I'll just tell you with this diagram. How do I find this solid angle? So basically what I'm going to do is, I'm going to take a small area ds here. I'm going to take a small area ds here. Then I'm going to join this area. I'm going to join this area by this line, but to this point. The area vector of this small area will go like this, but this line will go like this. So I will get an angle. Theta here. This angle theta will be equal to the angle theta here. So if I have to find the solid angle, this small solid angle that this ds will subtend, that will be equal to ds into cos theta divided by this distance r square? Yes or no?
Yes,
This
sir.
is how I will find the solid angle. Yes or no? Yes or no?
Yes, sir.
Now, if I change the question and if I put the question in this way, what is the flux? What is the flux passing through this disk if a point charge q is placed? If a point charge q is placed, what is the flux passing through this disk? If I ask you this question, you will do this question in what way? You will draw the point charge here. You will draw a small area vector here. You will see that this line is making an angle theta with the area vector. So what will you do? You with the electric field will go in this direction. The area vector will go in this direction. The angle between electric field and area vector will be theta. So if I write the small flux d phi will be E into ds into cos theta. Now this electric field due to this point charge will be 1 by 4 pi epsilon naught 1 by 4 pi epsilon naught into ds cos theta divided by r square. This will be the small flux passing through this small segment. Now you look at this small flux and you look at this small angle. You look at the small flux and look at the small angle. Finding out the flux is same as finding out the solid angle. Yes or no?
Yes, sir.
Because this entire term comes here. So basically, if I had to write the flux passing through this disk will be simply equal to 1 by 4 pi epsilon naught multiplied by the solid angle phi, multiplied by the solid angle omega. Because if I integrate this, I will actually find out the solid angle subtended by this. So what is the flux through this disk? Because of this point charge, the answer is very simple. If you know the solid angle, the answer is 1 by 4 pi epsilon naught. What was the solid angle? 2 pi into 1 minus cos of theta. You just put this value and you will end up with the answer. There must be some q here, charge q here, point charge q. Just put the values and you will end up with the flux. The flux will be q by 2 epsilon naught into 1 minus cos of theta. That will be the flux through this point charge through that disk. Do you understand this?
Yes, sir.
Okay, that is how you can find out the flux. Using the solid angle, you can find out the flux. Now, I can ask you a different question. Do we understand how I have done this? Yes or no?
Yes, sir.
Now, I can answer a different question using the same phenomena. So what I will do is, now I will rub this one out. Now, I will do this question in a different way. I will do a different question here. I will take this charge q out. Now the question is this. I have a disk. Whose surface charge density is sigma. I have a disk whose surface charge density is sigma. And you have a point P. And you have to find out the electric field at point P. I have already given you the formula for this. Electric field due to a disk at any point. Have I given you the formula? Yes or no?
Yes, sir.
Can anyone tell me the formula?
Sigma by 2 epsilon naught into 1 minus cos theta.
Sigma by 2 epsilon naught into 1 minus cos theta. Does it sound familiar? Now see, how do I find out the electric field? So what do? I take a small area ds. This small area is nothing but a point charge. I find out the electric field due to this point charge. Electric field due to this point charge at this point will be going in this direction, dE, yes or no?
Yes, sir.
Okay, my direction is not going right. So the electric field due to this point charge will be going like this, dE. Okay, if I take a point charge on the opposite side, the electric field due to that point charge will be going in this direction, yes or no? If I had to find out the total electric field created by this, the perpendicular components will get cancelled and the parallel components will get added up. This will be the net electric field, yes or no, bacha?
Yes, sir.
And this net electric field will be nothing but dE into cos theta, yes or no?
Yes.
Cos component, because this is also theta. So I can write this dE as dE multiplied by cos theta. Now what is this dE? This dE is the electric field produced by that small charge. And that small charge, what is the value of that small charge? Sigma into ds, that is the small charge, divided by the distance is r square, multiplied by k. K is 1 by 4 pi epsilon naught. K q by r square is the electric field due to a point charge. K q by r square multiplied by cos theta. To find out the total electric field, I have to integrate this. Once I integrate this, what do I see? I see cos theta, I see ds, and I see r square. Basically, I see this. Yes or no? So this is again the summation of their solid angle. So basically, the electric field due to this entire thing can also be written in this form. It is sigma by 4 pi epsilon naught multiplied by the solid angle omega. So whether it is electric field created by this sheet or whether it is flux through this sheet by any point charge, you can see both of these concepts are exact photocopies of each other. So you can remember both of this by simply remembering this solid angle. Do we understand this? So this has gone above what is saying bye bye, sir. This is going too much. Do we understand this? Yes or no?
Sir.
Yes or no?
Yes, sir.
Now, can I give you a question? Huh? Can I give you a question? Yes or no? Huh?
Sir.
Let's see, sir, if you can solve this. Anyone has noted this down?
Sir, one show previous page.
One show previous place. Low. Once I have shown previous place. Only once, no? Not twice.
Only one, sir.
Only once, sir. Okay, sir. Your wish is what my command. So you wish it, I'll get it. I'll get it done. Your wish is my command. Which question I was looking for? Looking for a diagram. Can I get the diagram? If I get the diagram, I'll present the question to you. And I hope remember it. And stay happy ever after. Everyone has noted this down?
Sir.
Paka?
Yes, sir.
Comes this legendary question once again. Yes? This one. We have already solved this question when the point charge was on the circular part of the disk, right? The circular part of this sphere, hemisphere, should I say. So here we have an hemisphere whose radius is r. As you can see, this is the hemisphere whose radius is r. Open hemisphere. When I place the charge at the center, I know the flux to the curved part is sigma by what? That q by 2 epsilon naught. We got this answer, yes or no?
Yes, sir.
Sir.
Now I place this charge here. Plus q charge is placed here at a distance r from the top, from the center of the semi-hemispherical cup. You have to find the flux through the curved part of this hemisphere. This is a question that I've seen in one of the JEEs. So when I say the curved part, I mean this part. You have to find the flux through this pink part of the hemisphere. How do you find the flux through this pink part of the hemisphere, which is the curved part of the hemisphere? Remember, the charge is not placed here. This is the center of the sphere. You can call this as C. The charge is placed at a distance r from this hemisphere. How will you find the flux through this pink part? Shall I help you, or you will be able to do this? How will you do it? Any idea? This is a question which may very likely come in your JEE. If they make a difficult JEE advance, this question can be a part of your difficult JEE advance. Shall I do it?
Yes, sir.
Okay, so how you got to do this is you again look at this green part. Now remember, there is no charge which is enclosed inside this hemisphere. Do you understand this? There is no charge enclosed inside this hemisphere. There is no charge inside this hemisphere. It's completely blank. It's completely blank. That means whatever electric field lines are going in, the same number of electric field lines will be going out. Yes or no? Same number of electric field lines will be going out. The same number of electric field lines will be going out. You have to find the number of these lines, which is the flux. Now it becomes a very difficult question to find out the flux through this curved path, because this curved path is curved now. But it is very simple for us to find out how many electric field lines are entering it, because the number of electric field lines which are entering it is entering through the circular part. Do we understand this?
Yes, sir.
So I just have to find out what is the flux through the green part. Whatever is the flux through the green part, the opposite of that will be the flux through the pink part. Yes or no?
Yes, sir.
To find the flux through the green part, you just have to use the simplest possible formula, and the simplest possible formula is, just saw it is, do you remember it? Q by 2 epsilon naught into 1 minus cos of phi, where phi was your semi-vertex angle. This is your phi, your ice cream cone ka semi-vertex angle. This distance is your r. That distance is also your r. So your phi in this case becomes 45 degrees. 1 minus cos of 45 degrees, and our answer is Q by 2 epsilon naught into 1 minus 1 by root 2. Do we understand this, bacha?
Yes, sir.
Everyone understands this?
Yes, sir.
Yes, sir.
Hmm?
Sir.
Okay. Now, there is one more question that I'm doing all sorts of questions that are possible on this. There's one more question, and if you can do that one, nothing like it. I have that question. Let me see if I have it here. If I have it in written form, that would be better. Otherwise, I will have to make it. Okay, I don't have it in written form, so I'll have to make it. Now the question goes like this. This is a cylinder, an open cylinder. That means it does not have caps on the other side. This is an open cylinder. The length of this cylinder is 2L. The length of this cylinder is 2L. You have a point charge Q placed exactly at the center of this. The radius of this is R of this shell. Now, remember this is an open cylinder. Does not have caps here. Okay, it's an open cylinder. You have to find out what is the flux to the curved part of the cylinder. I hope you can imagine this is the curved part of the cylinder. Yes or no? You have to find the flux through the curved part of the cylinder. This is the curved part, and this one is the circular part here. A cylinder has one curved path and two circular ends. Do we understand this? Yes or no?
Yes, sir.
So you have to find out the flux through the curved part of the cylinder. Now, can you do this? Because if you can do this entire flux thing is done with this last question. How will you find out the flux through this curved part of the cylinder? Remember, whenever any question comes, when they ask you to find out the flux through the curved part, you must think that there must be something that you must apply there. And whenever you see a circular part and a curved part, remember that you have to do something with the circular part. Because for the curved part, I can also solve it for the curved part and I can get the answer from there as well. But that will take a lot of time to solve, and you will not get that much of time in the examination hall. So there's no point of doing that question. How will I get the flux through the curved path? And for that, we will require some more information, which I have not done, but I think you know how to do it. You need to know some more information. So, how are you going to do it? Any idea? Okay, so what we'll do is, we will do this question after doing one more thing. So, to keep this question, leave 2 or 3 lines. Leave 2 or 3 lines. I will tell you something, and then you can probably go ahead and do this question. Okay? Okay? I still have 5 minutes. I can tell you that thing, and then you can probably do this question. So, what I'm going to tell you to do this to help you in solving this question is what we were waiting for so long. And what we were waiting for so long is the Gauss law. So I'll just go through this Gauss law, and probably that will give you enough ammunition to solve the previous question. Gauss law. Since we have talked so much about Gauss law, I know that you must be knowing a lot of things about the Gauss law. So what does this Gauss law state? What does this Gauss law state? Everyone knows this, right? Anyone knows what this Gauss law states? Yes or no? No one knows? I thought that since you have been talking so much about the Gauss law, you must be knowing Gauss law. No one knows? Boys? No one knows about the Gauss law. So I can tell you it is only valid for a closed surface, and Gauss law says that flux through any closed surface is equal to the total charge enclosed by the surface divided by epsilon naught. Gauss law states that electric flux through any closed surface. Remember, it is only valid for a closed surface, and that is why we had given so much of importance to this closed surface. Flux through any closed surface equals the charge enclosed by the surface divided by epsilon naught. Remember, this Gauss law is valid for all types of surfaces, but they must be what? They must be closed. If it is an open surface, Gauss law is not valid. Do we understand this, Bacha?
Yes, sir.
It's valid for all types of closed surfaces. Gauss law does not depend on size, shape, or orientation, how it is placed of the surface. No matter how you place it, Gauss law is valid. Gauss law is valid for all types of electric field. For all electric field. Electric field may be uniform, electric field may be non-uniform, electric field may be variable, this, that. Gauss law is always valid. Gauss law is valid everywhere. Anywhere in space, anywhere on the continent, anywhere on earth, it is valid everywhere. Do we understand this? But it is only valid on closed surface. So it becomes a very phenomenal law. I have this closed surface. This is a closed surface. This closed surface can be placed anywhere in this universe. Anywhere in this universe, you go and place this closed surface. If you want to find out what is the electric flux through this closed surface, now remember, this electric flux is created by electric field. This electric field is created by all the charges in the universe. Wherever there is a charge, it is creating electric field. Because of that electric field, electric flux is passing through this surface. If you want to find out the total flux, you don't have to find out the total electric field. How much is that electric field? You just open this surface. See how many charges are inside and divide it by epsilon naught. That will be the flux through this surface. But it is only valid when the surface is.
Closed.
If I open it, now it is not valid. Now I cannot find it. But as soon as I close this surface, Gauss law is probably one of the most powerful laws of this universe. Beautiful. Absolutely beautiful. Yes or no? Now, you can state this Gauss law in a different way. Now, if I write this, so I'll just write the statement so that you can go ahead with the statement in the next class. I can write this flux through the closed surface, bacha, as E dot ds. Do you remember this? I wrote in this way and then I put an integral and I put a gola over the integral. Remember this? And I told you this is surface integral of electric field. Do you remember it? Yes or no?
Yes, sir.
Sir.
So this surface integral of electric field is always equal to charge enclosed divided by epsilon naught. So you can write the statement of Gauss law in terms of the surface integral as well. So if you write it in terms of surface integral, it looks like this. Whatever surface you are applying Gauss law, that surface is known as the Gaussian surface. And now we'll be hearing this term Gaussian surface a lot. Gaussian surface is a closed surface on which Gauss law is applied. Any surface which is for that matter a closed surface, it is a Gaussian surface. So Gaussian surface is any closed surface on which this Gauss law is applied. Do we understand this?
Understood, sir.
Sir.
Okay. Now remember, this electric field which is coming in this Gauss law, this E is the net electric field. This E is the net electric field created by all charges of the universe. Do we understand this?
Sir.
This electric field is the net electric field created by all the charges present in the universe. But remember, Q enclosed only means those charges which are inside this closed surface. If it is not a closed surface, it is not valid. Do we understand this? Yes or no?
Sir.
Now, these are the points that I think given in your note, in your module. And this is already, I have discussed this. If you want, you can write them together at one place. I've already discussed this. Point number one, Gauss law is independent of the shape of the Gaussian surface as long as it is closed. Gauss law number two only depends on the total charge enclosed inside the Gaussian surface. Gauss law is independent of the position of charge wherever they are produced. The electric field is the net electric field due to all charge inside as well as outside, all charges in the entire universe. Then if the incoming flux is negative, the outgoing flux is positive. I already told you that. Do you understand this? Then one more important point that you have to remember in this case is if the flux is zero, that does not mean that the electric field is zero. It means that the net electric charge is zero. If you get the flux through any closed surface as zero, that does not mean that electric field is zero. The net charge can be zero. If electric field is zero, definitely flux is zero. But if flux is zero, electric field may not be zero. The net charge could be zero. Do we understand this? Yes or no?
Yes, sir.
Once you have this information, you should be able to solve this question with the information that you have collected just now.
Sir, one show previous page.
Alright. Show it once and I'll show it again and I'll show it again and then I'll show it again. You can note this down, keep it, and then try the question that we had done. This is probably the most difficult question that can come in your JEE. And I've given you that. It cannot be a question which is more difficult than this one. Okay, so I'll wind this class off here. I will also give you some important points still left. 1 or 2 more points I will give you with the Gauss law, with examples, how to solve questions. And then when we solve 1 or 2 small questions, then I will take you back to that question where you have to find the flux to the curved part. We have already solved the question. I just have to tell you the answer. So I'll do that in the next class. And we welcome Gauss law. And I think by 1 or 2 days, we'll be finishing question of Gauss law maybe tomorrow, and then we will see applications of Gauss law. Remember, we have to solve a question where the cylinder was there with a hole, and that spherical hole, and we still don't know what is the electric field of that cylinder. So unless we know the electric field of the cylinder, we will not be able to solve that question. How will you get to find the electric field of the cylinder? That would be done after Gauss law. So we'll do that in the next class. We'll try to complete Gauss law. Applications of Gauss law will be probably on Monday. We'll be able to start. So we'll do that. Take care. Have a nice day. God bless you all. Bye bye. If any doubt, you can always come up to me.